give me a minute. Whoops. Okay, now we're going to look at the some old DBH data with 4 families. There's something interesting is going to happen this time, I hope. We're going to use the ABO marker included in data sets in the release package. Whoops. Okay, let me. So what we're going to use for options, we're going to use multi-point, multiple marker regression. This means we're going to regress on multiple markers. We'll see what difference that makes. We're going to have the trait square root of DBH. We're going to use the regression method, the diff method. We're going to look at the 2 markers, ABO and AK1. Look at empirical p-values with the maximum rep set to 1000 and all other options left at default. Now, before we go on, let me just point out these 2 markers, ABO and AK1, are basically both on chromosome 9. Now, when we see what happens, then I will discuss that more. But remember, we're regressing on both of these. It is multiple marker regression. Okay. And I think this is where you take over.
Yes, this is to show how to actually set your multiple marker regression. Okay, so the first we do specify our trait to be like a square root of DBH. And then the sample mean, we can do the blob mean, any mean that you would like to, in case we did put the blob mean, which is the default. And then in next part, here we want to actually select just the marker that we want to regress together. Okay, so in this case, we click the ABO and AK1. Okay, and then just to we let it go, then we'll see our ABO and AK1, 2 markers are selected because those 2 are the one that we want to regress together. Okay, and then next we do check our type of the regression, and then since this is the multi-marker regression, we want to check in here, we want to select not a single marker but multiple marker for our type of regression. Okay, so then since we want to compute the empirical p-value, we do click the it's not true. Sorry. Yeah, we want to click the define, and then that's where we want to change our max permutation in here. By default, it's 10,000, but we wanted to actually do like 1,000,000 replicates right there. So you actually type in your value right there. Okay. Then, so all other sets, everything looks good. We want to do our dependent variable to be W4. Okay, everything looks good. Then we run to get this outputs. Okay, it's done.
Okay, so here it tells you you're using the continuous trait square root DBH, W1, which is typically set at 0.5 or 0.5 is going to be there. And what we're going to use, identity weights, no, robust variance, no, SIB-SHIP mean, no, use the BLUP mean. Okay. And then you've got all these this information. Now, if you look at the bottom, you can see there's ABO and AK1. And you can see the p-values about 0.0004 and 0.01. Now, let me So compare, it was 0.0014, 0.0091 empirical before. It's got much smaller. Now, why has it got much smaller? Well, the point is you're now regressing on two markers. So there is a smaller residual variance. However, you have to be careful when you regress on two markers. They have to be uncorrelated. Okay, now these two markers are linked. They're reasonably close, but they're not tightly linked. And therefore, because they're not tightly linked, if they were tightly linked, they would be highly correlated. But because they're not, by doing this multiple marker regression, you reduce the error sum of squares. They're not correlated. And so you get a smaller p-value. Okay, let's see what we have next. We can now do another set of options. We could do multi-marker regression with square root dBH. We can use the diff. Now we can use these two markers, AK1 and C3, which it says they're unlinked. They, AK1, I can't remember if they're both on the same chromosome or not, but they're certainly not tightly linked. And we're going to do max replicates and 10,000, everything else at default. So let's try it now.
So same thing as before. In here, we do define our trait. Okay, and then we already defined it, but now at the marker selection, instead of like ABD and AK1 in the previous example, now we do check the AK1 and C3. And now next we want to define the computation ones, right? Okay, oops, sorry about that. Then we want to make sure that we do have the same dependent variable as before, so that we can actually compare with the previous examples. So by doing that, now we do get the similar result, but looks like a similar, but with a different, the one for the AK1 and C3 multiple.
Right. So now what we see is that the p-value goes, let me see, is it, I'm trying to see if it's, you've got multiple marker regression. You see, we need fewer replicates for AK1 and C3, and the significant levels go down even more. So if we look at the next slide, so what we see here is the summary of the results. If we do single marker regression for ABO, AK1, and C3, we get these values. On the other hand, if we do multiple marker regression, we notice that the ABO and AK1, they stay about the same. AK1 gets a little bit smaller and C3 gets about the same. So it depends. Sometimes you can get much more significance by doing multiple regression, but you've got, and that is when I say multiple regression, I mean regress on multiple markers. That's what I mean here, multiple marker regression. And sometimes you don't. So let us consider now causes of numerical instability in generalized least squares. So if you have linear dependencies in your data, that will cause numerical instability. And this can be removed by dropping unnecessary extra variables, covariates, allele sharing at tightly linked markers. That's one thing you can do. You can also get numerical instability where you have near singular correlation matrices. And that can be resolved by fixing some correlations to 0. And basically, when you're going from capital W4 to W3 to W3 to 1, you are estimating fewer correlations. You're fixing some to 0. And that is why you get less instability. And there are limitations of the model fitting algorithm. So these are the checks you would do. You'd look at the regression coefficient, the test statistic, the total residual parameter variance estimates that are disproportionately large or small relative to the scale of the data or the number of observations. That's number one. If they look completely out of the ballpark, then there's something wrong. The other thing is that when performing multiple regression, parameter estimates that are alternating in sign, these oscillations indicate strong linear dependencies. So if you see those alternations up and down, that is a warning sign. And when performing a multi-point analysis, parameter estimates for closely spaced markers are quite different. If you see that, that's another warning sign. Look at this picture and you can see there's a lot of instability. These are, you can see lots of peaks relatively close together, and that is not the way it is. And you can see they're huge peaks. I'm trying to think if you can look at the scale of things. Whoops, no, it doesn't. Yeah, there you see the scale, 15. That's way out, way up there. Okay, so now let's look at the maximum likelihood analysis of affected relative pairs. So this models the recurrence risk in the conditional logistic regression to give multi-point LODs. Okay. What is the relative recurrence risk, lambda R? It's the probability that a type R relative of an affected person is affected divided by the prevalence of the disease. So it's the recurrence risk, and it's relative because you divide by the prevalence of the disease. And if we make it as a function of X, it's the recurrence risk for two relatives of type R at a covariate value X. And this is one of the main things about this model is you can do it at a covariate value. Okay. How do we compute lambda S? So lambda S is the SIB recurrence risk ratio. And at a particular value X, it is a quarter plus a half lambda 1x plus a quarter lambda 2x, where lambda I is the recurrence risk ratio for two relatives who share I alleles identical by descent. So that's a quarter plus a half. The relative risk, the two relatives share 1, lambda 1 at the value X, plus a quarter, lambda 2 is the recurrence risk ratio of two relatives who share two alleles identical by descent. And all this at specific values. So lambda S, these are values at specific values of the covariates. And that can often be extremely helpful in detecting things. Remember, the covariates is always centered. So let's look at the program LotPal. So LotPal is a bit like SIBPal and RelPal, but now we're doing it in terms of LODs. So LotPal performs an affected relative pair linkage analysis. There are 1 and 2 parameter models. The 1 parameter model can have covariates and the choice of constraints. So there is a default that corresponds to halfway between recessive and dominant. If you know you could make it recessive and the alpha is very large, like infinite, you make it 100 or whatever. If it's dominant, alpha is equal to 1. Now, if you read the manual, you'll see this all comes down from a paper by Whittemore and 2. And what I want to say is, even before I read the paper, I heard Alice Whittemore give a talk on it, and she admitted the paper was almost impossible to understand. So be very bold if you try and look this up, and be very clear the difference between A and alpha. These things wander around. Right, so what covariates might you have? You can combine discordant, concordant, or affected SIP pairs. That is by adding a discordance or covariate. And then you can also have diagnostic output. So let's think about incorporating covariates into this LOD. There are multiple ways to include pair-specific covariate values into a LotPal analysis. You can put it in as the product of the pair, the default be mean-corrected product. So you remember you have a pair and you have a covariate, and you can just put in the mean-corrected product. You can also put in the sum for the two individuals. You can put in the difference for the two individuals. You can put in both. You can put in an average. And you can put in just one, the first member of the pair. And you can mean center the covariate value of any of the above. And there are certain problems that arise. By the way, before that, you can put in like squared or cubed or product power of any one of the above. Okay, these are the problems, the limitations. So you've got all these covariate values in there. So first of all, the current test only includes support for a single disease locus. All right. Covariates cannot be added if you're going to do the affected SIP pair, discordant SIP pair model, because that in itself is a covariate. You can't put any more in. And here is the LotPal. And I believe this is where, is this where you take over again, Joe?
Yes, I can do that.
Okay.
Okay, LotPal is the program that, just like I was explaining when you're doing the SIPL, it needs the IBD file from the GenIBD, and then it gives you the INF file and the analysis result file. Depending on the options, you may have more than one analysis result file, especially summary and detail and other part. And also, same as like the SIPL, it also gives you the R script file that which you can actually use to plot. Okay, this LotPal demo, we will actually use a little different, another data set that is actually also included in the S.A.G.E release packages. This is the prostate cancer data, and the options in the following example is actually it is the binary trait. There is a cancer case or control, and then it uses the Gleason score as a covariate. It's like we'll use the sum of the Gleason score from the two individuals in a pair, and all other options are left as default. As you can see now, we do populated the drag and drop the LotPal job under the job. Okay, then we do have the prostate cancer file and the data file dragged in, and then we are using the GenIBD output from the GenIBD run right there. So you can see the all three output files already. Okay, and then we do click next. Then we go to this analysis, the definition panel. First, we do wanna make sure that we define our trait of interest. So by clicking define, then we do get this, the trait specification panel window. then you want to make sure that you choose the name of the trait, which in this case, in our pedigree file and the parameter file, we named it as a cancer. Then by default, when this is not a binary trait in pedigree file, it will actually automatically make it as a binary by using this cut point 0. So if you, let's say this cancer was actually a continuous the variable, then if anything that's less than 0 will become like the unaffected, and then greater than 0 will become the affected. Okay, and then there are 3 different types of like analysis that you can do. We are doing the affected relative pair analysis. Another cases that you can actually do affected relative pair and discordant sibling pair, while others as well. Okay, then next we do have the define the trait. We wanna select our covariates by clicking the define. Then in here, we want to actually select our covariate of choice, which is the Gleason score in your data file. Okay, we want to use the sum, and we are not doing any power transformation on the covariate value. And we are using the mean centered, and everything looks good. Click the add the covariate, then we will have this covariate added in there in our model. And once it is done, we can click run, and we do get this LotPal result. Bye.
Now, what you need to know, for those of you who don't know, the Gleason score is the severity of prostate cancer. So it makes sense to put that in as well, and to hope that that will give you more power. And this first score, it says concordantly affected relative pairs. That's what we're doing. But we're putting in a covariate, the Gleason score, and we're putting in the sum for 2 individuals, which is exactly the same if you think, because it's mean centered. It's really the same as the mean. The sum and the mean. It's not going to make any difference to the p-value you get. Is just going to make a difference to what you get as a covariate. And we're going to use the 1 parameter model constraint alpha equals 2.634. This is the parameter alpha. Let's look at the next slide. Oh, you can see that after centering, it does get the right mean. Now, if you look at this, note the default alpha corresponds to A of 0.275. When you read the papers, at least when I read them, I get completely confused. But that's the whole point. That's the one that's a compromise between assuming dominant or recessive inheritance. And if you had a good reason for assuming dominance or recessive, you would. But this is and be very careful, there's the alpha value and the A value. And if you think about it, A is 0.275. That is sort of between dominance and recessive. If you go around and find out what A is, the alpha is not so clear to understand. But I just warn you, it's a good paper to look at, but not easy to understand. All right. Whoops, where am I? There's a lot of diagnostic information that comes out. LotPal allows the user to output a file that includes for each pair in the analysis at a particular marker, the family and pair identifiers, the type pair, the estimates of sharing 0 or 2 alleles identical by descent, the covariates, and the log score contribution for the pair. And basically, you add up the log scores for the pairs. LotPal also prints a histogram of the log score contributions, and you get the empirical estimates of the covariance matrix of the parameter estimates. So you can see that. Okay. if you are going to use, we'll talk more about the LotPal, the model underlying it tomorrow. No, when I say tomorrow, I mean the day 4. Now I want to talk about model-based linkage analysis, and this is the classical 2-point linkage analysis. Okay, we call it single marker, but it's 2 points because there's a trait and a marker, and the marker has to be what is known as a trait marker because it acts like another trait. And the program we use for that is LodLink. So it performs the model-based 2-point linkage analysis. It requires specification of mode of inheritance. You'll see now how we can get around that later, but it's important to realize there must be somehow a specified mode of inheritance. It can perform linkage analysis without assuming independence of pairs. It takes the whole pedigree structure, takes the whole large pedigree, and say this is the classical original LOD score analysis. And you've got to specify a genetic model. You can create your own trait model description file, or this is what is beautiful. You can use the output from SEGREG. SEGREG, remember, does a segregation analysis, and maybe one of your analyses said, hey, we have a major gene model here. And what it will do, this program SEGREG will output individual specific penetrance functions, probability of Y, particular Y, given its genotype. Okay, so typically we have 3 genotypes, the UI, and you'll have a probability of Y given each of them. We'll discuss that either later today or the next day, I can't remember. But let us first look at the tratus locus description file. This describes the underlying trait locus, a mode of inheritance to be used in the model-based linkage analysis. I'm now going to assume, first of all, that we put this in. This is what we used to do a long time ago. You have to put this stuff in. We haven't got any SEGREG results at all. For example, suppose we have a trait we'll call disease, okay, and an underlying model with 2 disease alleles. Allele 1 has frequency 10%, allele 2 has frequency 90%, okay? And we have 2 phenotypes, A for affected and U for unaffected. And let's suppose allele 1 predisposes towards the expression of affection and is dominant to allele 2, okay? So the penetrance table may look something like this. A and U are phenotypes, and it's saying if you are affected, the probability of being affected, given these 3 genotypes, it's saying for 1, 1, it's 1, for 1, 2, it's 1, for 2, 2, it's 0, and the probability of being unaffected is 1 for 2, 2, and 0 otherwise. This is simple Mendelian recessive, that it's fully penetrant, no sporadics. This is the simplest possibility. I mean, simplest in that, because it may or may not be true, but if it were true, there's very little to worry about in terms of putting in unknown parameters. Note there is no limit on the number of phenotypes possible. Here we have only 2, affected and unaffected, but we could have lots of phenotypes available. Or we could have somewhere that's, I don't know, different kinds of severity. All these are possible. So this is an example of a trait locus description file. What this says is that allele 1 has a prevalence of 0.1, or that's what we would call the allele frequency, and allele 2 has a prevalence or frequency of 0.9. And A affected is 1, 1 or 1, 2. In other words, A is dominant to unaffected 2, 2. So this is the general setup is, and then what you have to realize is that you must match the coding you have for your trait in the pedigree data file. Remember what you see, I don't care, whatever it is, whether it be a trait or a marker, you only observe phenotypes, and they must be in what's in your data files. Here in our data file, we have A and U for affected and unaffected. All right. Now, suppose you've done SEGREG and you ask for a type probability file. This is automatically generated. You can't edit it or don't edit it. But this file will come out and it has things, it'll tell you what your model was. It'll tell you your analysis model. It says you have 2 alleles and these are the frequencies that turned up. Now, you'll notice we're assuming we have 3 genotypes. And for individual 1, which happens to be a founder, we have the 3 genotypes possible, of course, AA, BB, AB, and BB. And it says their penetrances are those 3 values. In other words, the probability of being AA or BA, this first one, basically it's unknown because it's a founder. Now, you can also get, because you remember the posterior genotype probabilities. In other words, once you've looked at the whole family and you've stuck in the various estimates that you get at the end, you can now, after the analysis, after putting in those maximum likelihood estimates, you can ask what is the probability that a particular individual has a particular genotype. And you'll see here, these 3 here for the first individual are 0.32, 0.65, 0.02. This is all based, remember, likelihoods are proportional to probabilities of the data. So you can get these posterior probabilities. This file has both things. It has these posterior probabilities, which you might be interested in. You might be doing some genetic counseling and you want to know what's the probability a particular individual has a particular genotype. Okay. What's his probability given not just his genotype, but the genotypes of everybody in the family and the genetic model that you hope fits the family. If it doesn't fit the family, you wouldn't want to put it there. But it's also got these penetrances, as we call them, and this has got under whatever model that you have come up with. You've done a segregation analysis. You said this one fits. I want to use these penetrance functions that come from this model in a linkage analysis. So you ask for this file, the probability type file. And you'll see, first of all, this is the file name that has to be included in the LODLink analysis. And then we actually go into LODLink. I'm not sure if I continue or not, or let me have a look. LODLink program with the old DBH data for FAMS. Do you do this or do I do this, Yanju? Tell me.
I can go from here.
Well, I mean, I can. Oh, well, we're going to look. Well, we're going to look at square root DBH because we happen to know something about this, and we're going to take it model name DBH3 mean from a SEGREG file. We're going to take that from there, and we're going to say we want sex-specific recombination fractions. That's what it says there, but I don't think we do in the output. I think it says they're not sex-specific, as I recall. And then we're going to ask for Smith's homogeneity test. There are several homogeneity tests, and I'll talk a little bit about them when we see some results. And all the other options are left at 0. So you take it away, and then we'll see what comes out.
Okay. This example, we are back to the familiar phase of this analysis panel there. And we just loaded up a large link job. And then in this case, we are using the same, the DBH, schizophrenia DBH data file, then the example file that we have been using. Excuse me. So in here, that right here, you see we have a parameter file and the data file and the marker locus description file. Okay, all the marker location that we want to do the linkage analysis. But then we do have to have one more, either trait locus file or type probability file that Dr. Houston just talked about. Okay, so that's where, since we are in this example, we are gonna use the type probability file. We do click there and then finds the type probability file, which is a output from the S.A.G.E. So you see that in my example that I do have this like a S.A.G.E. one job that I did previously. And then there something called like type T, the S.A.G.E. 1.typ file. That's the one that we're gonna use in this example. Then we go to the analysis definition panel. Right there, we first make sure that we are actually specifying the model that actually correspond to the type probability file, the model that's in the type probability file. So we are making sure that we are using the type trait marker model, which is coming from the .pyp type probability file. And we want to make sure this S.A.G.E. 1 actually matches the right at the beginning part of the type probability file. This is the model, that the name that we want to make sure that we matches this. That's how it actually finds the trait locus that we want to analyze. Okay, but then in case if it is the trait marker is coming from the marker locus file, then we would choose this one. Okay, and then different linkage test options that you can choose from there. And we want to do the Smith's test of the homogeneity there. Okay, and in case use the sex-specific combination fraction, we'll click right here, use the sex-specific combination fraction. And then when it's all ready, we can actually click the run to get this large link outputs.
Okay, this output, the first thing we notice is the name from the .type file model. This is what we got out from S.A.G.E. We have this name up here at the top. It says LOD scores. Yes, we want LOD scores. Linkage tests. It says yes, we do. Sex-specific recombination fractions. Yes. And assuming homogeneity. But on the other hand, so that the LOD scores are obtained assuming homogeneity, but we're going to test for homogeneity, and we're going to use Smith, that's Cab Smith, C-A-B Smith. Those of you who may know the name, he was a long time at the Galton Lab in London, and it says we're going to use his. And are we going to use sex-specific recombination fractions? No. Morton's test, we're not going to do. And genotype probabilities, we're not going to get those out. Okay, so I'm not going to, I don't know whether it's later today or the next day. We're going to talk about I think it's next day, we're going to talk about the different tests for homogeneity. But right now we're going to look at this output. This says the recombination fraction selected for sex average. We're looking at the values 0, 0 0.1, 0 0.01, 0.05, 0.1, 0.2, 0.3, and 0.4. This is the typical kind of thing we used to years ago. We would just calculate the LOD score at different fixed values of the recombination fraction. And we seen that we're going to look at, first of all, the ABO locus, and we get these LOD scores, and you can see these, they're 4.05 at 0, 4.81 at 0.1. That looks pretty high there. And then it gets slowly lower as you get further away. And you can get the maximum likelihood estimate. And you will see for the ABO locus, you do various tests, and then you can get various p-values, chi-square tests, and what have you. And for Smith's homogeneity test, we end up with a p-value of 0.5. That doesn't seem right. I think there's a little bit missing at the bottom underneath that. But anyway, you get all this detailed output, and we shall talk much more about that. I think it's the next day. Let's look at the next slide. Detailed output. Okay. So this is, it does it by constituent pedigree. Remember, what you do is you calculate LOD scores for each pedigree, and then they can be added up over pedigrees because we assume the pedigrees are independent. But you have to add up the LOD scores at specific recombination fractions to get the final result. So we can see this is, we have here different, you see, containing pedigree 1 contains member 1, and we have all these results here. Okay, so that's pedigree. This is by pedigree. Okay, let's continue. Also, okay, it says don't forget a constituent pedigree is informative if we do not have a unique. I mean, the thing is, we have to assume that it is completely independent, even though it's somewhere in the same family. And so it's informative. It's more informative information, more information. So let us look at this summary slide. So here's a summary of the maximum LOD scores for 4 DBH models. Okay, these models, remember, we obtained the type file from each of these models having fitted in S.A.G.E. So if we assume it's codominant without familial correlations, we get a LOD score, maximum likely estimate of theta, as the LOD score's 4.8 at a recombination fraction of 0.014. If we put in some familial correlations, it goes down to 4.4 and a recombination fraction of 0.016. And next time, if we put in some correlations, codominant with familial correlations, and it doesn't make, let's see, sibling, and I don't understand that. I don't understand that third one. I don't remember exactly what it means. But here we have a lower LOD score and recombination of 0.02. And if we have the spouse correlation is 0 and a parent offspring equal to the sibling correlation, we get a LOD score of 4.7 and a recombination fraction of 0.147. So the two large ones are the top one, codominant without familial correlations, and co-dominant with no spouse but a parent offspring equal to CIP correlation. They have LOD scores of 0.48 and 4.8 and 4.7 respectively, and the recombination fraction is 0.04 to 0.014 to 0.015. So this is very significant in a sense. You know, we used to say a LOD score of 3 is so-called proof of linkage when we were doing these kinds of analyses, just a few markers. So this is really, at the time this was done, when we had a relatively few markers, maybe only 20 markers, maybe 30, this was really very significant. Okay, it's already lunchtime. Wow, we've gone pretty fast, I think. What is the time? It is
almost noon now.
And we start again, what, at 1:15? Is that
1:10, yeah.
1:10. Well, first of all, are there any questions? I haven't heard many questions. It's like you understand it all. It maybe it's not that you understand it all, but you're thinking to yourselves, well, this is old stuff. We don't do that anymore. Well, we do. And when you find that you've got something segregating in a Mendelian fashion, we do use the original LOD score analysis. One of the things I think that is unfortunate now is everybody is only interested in association analysis, but I think linkage is very important. If you have the right data, pedigree data, and you happen to fall upon a trait that segregates in a Mendelian fashion, which, you know, this is what you want to do eventually. Remember, think about it. You may be doing association, but that doesn't tell you much if you don't know how the segregation is going on. So I see something in the chat.
Yeah, and I would like to say, to add to that, Robert, and that is, yeah, people say it's old school, but that was before sequence analysis.
Right.
And now that whole exome and whole genome sequencing have become so affordable, there has been a renaissance of both non-parametric linkage, like you talked about earlier, and currently parametric linkage analysis. And there are many, many people finding genes for rare Mendelian diseases, but also who are using parametric analyses with models that are appropriate or best guess models. You and I both remember Neil Rich's guess lot approach,
Yes.
But there has been a lot of work done showing that if you have a parametric model that is close to the truth, and this is the important and for all of your marker loci, you have good estimates of the allele frequencies,
Right.
then having a good guess at a parametric model is a very useful approach. So we have started doing linkage analyses again in all of our family data that now we can finally afford to do whole genome sequencing in.
Yeah.
So these methods have had a big revival, and in fact, people are doing methods development again in
Sure.
linkage studies. So that's why I think this course is so important right now, and it's why all of my trainees will be watching it. I teach this stuff at NIH now because and people actually in my classes now are going, yeah, we're doing this for our traits. Wait, how do we do this? How do we do that? As opposed to, 5 or 6 years ago when people were like, oh, family studies passe. There's been a huge sea change of people understanding this is a tool that's useful when you have all the variants in the genome. You can do
Sure.
2-point linkage again.
That's right. That's right. Now, I saw Alexa had something up on chat, but I didn't see what it was. It's disappeared. Is that a question? It's disappeared from my screen. There was a chat.
Yeah, it says, could you talk a bit about individual specific penetrance?
Individual specific penetrance. Well, it's a penetrance function, and it's what it is. It's saying, given all the data you've put in and the model, what is the probability that an individual with this phenotype has this genotype? It's the probability of phenotype given genotype. That's what it is. And you need it. I don't know what else I can say. It's individual specific because in these, it's using all the information you have on the individual, and when you're doing a pedigree segregation analysis, you are in order to do linkage analysis, you need to put it in, and you can. This was a trick that we thought up a long time ago as, hey, we've got all this information after we've done a segregation analysis. Why don't we just get it for each individual on the basis of all this data and use it as a file to go into linkage analysis? It's basically saying, taking all the information you have in the pedigree, the relationships and everything, and given all that, what is the probability of a genotype for each, of a phenotype for each genotype, or the other way around? I mean, penetrance, the probability of phenotype given genotype.
Well, so, and yeah. Robert, doesn't all linkage analysis does that based on your parameter file? So if they put in the parameter file by hand, then the linkage program will calculate exactly those penetrance functions. You just don't see them, right?
That's correct. That's exactly right. And it's a neat trick because it says, look, you've done this segregation analysis. Why don't we get a particular penetrance for each individual? What's the probability for all the, typically there'll be 3 values because you'll be assuming 2 alleles at one locus. It could be more, but typically you'll have that at the end of the analysis, because when you do segregation analysis, typically you're assuming 2 alleles at one locus. I mean, it could be more, but that would get too many parameters to estimate. So you've got all that. You've done all the analysis. You've got all the maximum likelihood estimates. You can put everything in, and then you can get it individual specific, and you don't have to put anything else for the locus description files or anything like that. You don't need it. You've done it.
It's basically just a shortcut in terms of your parameter input file, right?
That's
because
correct.
You could take the results from SEGREG and by hand put them in as the parameter file, the penetrances, the allele frequencies, etc. And then the program would have to calculate exactly what you've done this way. This way you don't have to put it in.
No, there's a little difference because this is individual specific.
Right. But within the linkage program, when I give it the parameter file from the segregation analysis, the linkage program itself calculates those individual specific trait locus penetrances when it's calculating the maximum likelihood, right? It's just a shortcut.
Well, I'm not sure that's correct.
You don't think so? I thought it.
No, I think this is Alexa's problem. Why do I say individual specific? Because it's using all the information and it's saying, it's if you were to put in just a locus description file, it's saying it's the same for everybody. But we're saying, no. We can do it individual specific using all the information and the genetic model. That's the whole point. It's doing something more powerful. That's the very important. You're not quite right, Joan. It's not just a shortcut. It's more than that. Because it's saying each individual has a probability of being a different genotype.
Right.
And similarly, it has an individual probability of being a phenotype given each genotype. And so it's putting all that in together. And it allows for whatever familial correlations you had in your model, anything like that. These are things that couldn't be done just from a simple locus description file.
Oh, so what is it using to get that individual? Yeah, so all right, sorry everybody, we're getting into deep algorithmic discussion here. What is it using
it's using
from the segregation analysis model to give you a different penetrance given genotype
for each individual?
That is a difference. So where's it getting that from? How's it doing it? Tell me, I want to know. Sorry, everybody.
That's okay.
Yeah, I'm geeking out here. Sorry.
Yeah, well, it is. It's you have to think about it. You're using the whole family structure to give two things for each individual. You can determine the posterior probability an individual has this genotype, and what's the probability it has a phenotype given this genotype, and all the rest. I mean, I don't know how better to put it, but it is individual specific. It's getting more.
Okay, well, that's interesting. We'll have to
think about it
into some other time when we're not holding all these people captive. We'll have to get deep into where is that information coming from. That's interesting.
Yeah, it is, because it's using the best, like you know, when you do a segregation analysis, one of the things, and that was in the original Elston Stewart paper, it pointed out how you can, for each individual, find the posterior probability of that individual's genotype. And by the same token, you could say, what is the, you can get an individual posterior probability, the probability of phenotype given the genotype. You can do that. It's these posterior probabilities obtained from sticking in the maximum likelihood estimates, which are based on not just, I mean, you're using the whole family structure.
Right. Okay.
Point.
That is really interesting.
So you get more power than you would from putting in just one locus description file.
Okay, cool.
Yeah.
That's exciting.
It is exciting. And not only do you get more information, but it's easier too.
Well, it's easier too. I just thought it was good because it was easier, but
well, once you've done a segregation analysis that fits, it's very simple. That's the whole point.
Now, of course, that's going to assume your segregation analysis is really appropriate for your linkage families.
Absolutely.
So you want to be sure they're from the same population, et cetera, et cetera.
Absolutely.
But okay, that's pretty cool, Robert.
You see, what you want to do is linkage in the same families that you used for your segregation analysis.
Yeah, how that doesn't happen very often, though.
Well, then this won't help you. If
well, for quantitative traits, it happens a lot.
Yeah.
For disease traits, not as much, but for quantitative traits, absolutely. Yeah.
That is why you could, instead of having affected, unaffected, you could have severity of disease, like a Gleason score.
Yeah. But
Yeah.
But again, you tend to ascertain on there having been a disease.
Ah,
and
you've
for
got to get the
linkage,
where you
yeah,
have to have the
right.
ascertainment
For
right.
linkage, you generally ascertain not just one case, but an aggregated family, so it's informative.
Absolutely.
So,
We'll talk
yeah.
about that too.
Yeah.
In fact, we
Yeah,
already
yeah,
have a
yeah,
little
yeah.
bit. We'll talk a bit more about, you know, how, and it's not, you know, I'll say right now, I think there was a, early on, I don't know, it was the first day or second day, there was a paper by Ginsburg that was referenced for pedigree analysis. And I'll say that that paper is not easy. And if you really want to know, though it's not easy, far better is the book, which I'll be happy to send anybody a PDF of this book by it's Ginsburg, Malkins, and myself. If you
Send me a copy, Robert.
Absolutely, it's got there right. It's tough going, but it's
wait. You made us prove every equation in your Gott's linkage book. I understand about tough going.
Well, that's right. And you know, as you know, and I don't want to criticize you, Gott.
We found typos. Yeah.
No. But this, you know, he talks about the phenotype. What did he say? I can't remember. The apparent phenotype. Well, no, it's a phenotype. Well, if a phenotype is what appears, there's no such thing as an apparent and a non-apparent phenotype. But he does, and I can see what he's getting at, but it's just not the right way of saying it. You know, or apparent. I can't remember what it is, but yeah, in fact, I will say your God has done an enormously good for the field.
Oh my goodness, yes.
And the way we all learn is by reading the others and saying, you know, that's not quite right. And we all learn. I suppose we did go through that book, didn't we?
We did. Every equation was proved.
Yeah, you have to.
It was good training.
Yeah. So anyway, that's been fun. Sorry, Andrew. Yeah.
There are a couple of demands for the books. So if you can send me over, I can send it to the people who requested it.
Okay, I'll send it to you. Well, I'll send it to. Okay.
Well, I will send the list of the people who actually asked for it then so far.
Oh, there have been a lot of people ask for it. Okay. Then
and there are more than one people.
Oh, because they don't know my email address. That's okay. That's good.
Yeah, and which actually includes me.
Includes you. But I got to warn you, and he does things and he says these are approximations. You know, it's a remarkable thing because until Ginsburg started thinking, what do you mean by a pedigree? What is a pedigree? I mean, you know, it's the whole population if you go to Iceland. So it's not a trivial question. What do you mean by pedigree even, you know? And these are cause difficulties when you don't know. I mean, at least, you know, it's there's a whole, in statistics, there's a whole theory, sampling theory.
Oh, gosh.
But, you know, it assumes your sampling units are discrete. And in genetics, they're not discrete. They're all over the place. You don't know what you've got. You know, a SIP ship, you can say, okay, a SIP ship is discrete. You have so many SIP ships. But think of a nuclear family. Think of a nuclear family. Well, there are the children and the parents, but those parents could be the children of another nuclear family. And so it's all very peculiar that you don't even know what your sampling units are. That's the problem. If you go to sequential sampling in statistics, it's so easy because they know what their sampling units are. We don't even know how to define them most of the time. And we'll see that when we get to S.A.G.E, I think later today. It's a very peculiar situation, very peculiar what we're doing. And I think it's great to have people who are accustomed to classical statistics to get thinking about these problems, because we have real problems in genetics. I don't want to say we don't know what we're talking about, but it's almost like that. Anyway, okay. So yes, I will send you that book, Yanju, so you can send it off. Remember, it does have errata at the end. So you might want to go through. I don't think I corrected the actual book itself, but you might want to go through and I don't know whether you want to print it or not, but anyway, it's whatever it is. I had great fun with Emil Ginsberg, trying to help him clarify things. But okay, so we will start again at what? Do you say 1:10?
Dr. Houston, before we go, there is a follow-up mention from Alexa that about the individual specific penetrance questions, that she said, I am asking about the meaning of the penetrance, given you already know the individual's phenotypes. What do you mean by that, the individual penetrance, since you know your phenotype already?
Well, it's the probability of that phenotype given, say, one of 3 different genotypes. What's the probability of the phenotype given the genotype? But why it's individual specific is because you have other information about the individual, not just his phenotype, but you also know, and this is we're also saying we know this family structure and where that person is in that family structure, and that gives us more information as to the probability of his or her phenotype given his or her genotype. That's the whole point. You have more information. And there may be covariates in the model, all sorts of things. And you may have allowed for. So if you look at it, think of it when you're doing a segregation analysis, you can get every information on every individual conditional on every other individual in the pedigree. And each one is individualized. So you can talk about the penetrance for that individual, given not just his genotype, but also all the other information in the pedigree. So that's what it is, if you want to put it that way. Okay. And I say given, you're given also, you're assuming that everything else in the pedigree is how the structure and how they're related is all you, and how each one affects each other. You're assuming all that is known, of course, from your model. I saw a thing briefly come up, I think, from Alexa. I didn't see what it said. What did it say?
Okay, it says, I think this is what the fitted model would predict about the individual, given each assumed genotype and other information.
Yeah. As other information too. Absolutely. Absolutely. That's it. It's using not only that individual's genotype, but all the other information. So if you want to be more specific, this individual, it's the probability of this individual's genotype given a probability of the phenotype given this individual's genotypes and the genotypes of all the other individuals in the pedigree and where that individual is in the pedigree. Okay, it's much more. Yes, Alexa.
I was just, it's just awkward for me to sit where you can hear me. I was just trying to, because I would think that naively you would look at this and say, why are you giving me a probability of being affected when you already know if the individual is affected? And I'm saying this is what the model, taking all that information into account, would predict.
Yeah, it's a predict. Yes, it would predict. That might be a better way of putting it. Yep.
I just think it might be confusing to a lot of people to interpret what you mean by penetrance when you already know the fact.
No, you're absolutely right. It's prediction on the basis of all this data.
Right.
What you would predict. Yeah. For each individual. Yep. That's right. So it's not, in a sense, it's not penetrance in the sense, in the usual sense. You're right. Yep. Good. Thank you.
Thank
You
you.
clarified. You show me I'm wrong, which is good.
Not wrong, we just need the explanation.
Yeah. Well, no. I mean, it's bad. You could say that I've used bad terminology. That's right. Yeah.
So then is it right to think that it is, since it's a binary trait, then if it's a binary trait, then it is the predicted like a liability, underlying liability?
Right.
Well,
Sort of. Yeah.
yeah.
If in those models where you have infinite liability classes, because you can
Sure.
like make liability classes for every individual in the liability class models. So
Right.
it's
Yeah.
sort of like that.
Sort
yeah.
of like that. Sort of like that. Yeah, sort of. We'd have to think very carefully as to how to rename it. I'm not sure how. I'll let you think about it. But I think I think Letz's idea, it's the predictive probability on the basis of all you know,
Right.
what that of what you know about that individual, if that individual had the three different genotypes.
Right.
That's what it is.
Yeah.
Of course, that individual only has one genotype, but you don't know what it
Just
is.
don't know which one.
Yeah, you don't know which one, so you have to separate it out by genotype. Hey, this has been a good discussion. Thank you for helping me think things through. Yep. So
And there
We
is a-
miss having
one
these
more.
discussions with you, Robert. I miss it every day.
I know. Well, but I'm getting old now, so you've got to remember I don't have the memory I used to have, and I don't think straight. So you've pointed that out, which is good.
I don't know. You taught me new stuff today. So, hey,
Well,
good.
that's only because you made me think about it. Yeah. Well, I you know, that's why I like to have questions. And I don't know if I told you once. I'll tell you this story. Maybe I've told you this story. I tell so many stories. I had a student once, and I was going through the dissertation, and I said, I don't understand this. And she said, how clever of you. It's wrong. If you don't understand, there's something wrong. I mean, most of us, we know it's not our fault. It's the speaker or the writer. They're not making it clear. And I must admit, calling an individual specific penetrance is not clear. I will admit that. But it's what, given all the information, what you would predict for that individual, if that individual had one of the three different genotypes.
Right.
So it's sort of genotype specific. Yeah.
There is another one that, are there any other books that you'd recommend for reading? I'm sure there are many, but if there is more.
Well, we have at the end of this today, we'll see lots of books, though they're all, I mean, you know, I think you need to understand the early books, and we'll see some at the end of today, some books that I've recommended people look at in general genetics, because, you know, a lot of people doing genetic epidemiology these days have never learned classical genetics. And I think a good grounding in classical genetics is very important.
Yeah.
I mean, in a way, the Ginsberg and Malkin's book, I mean, you're going to find it tough going, but you'll understand the difficulty. And which reminds me, and I don't think I've said this, if any clever statistician present, you've probably heard of the, oh dear. Well, I'll think about it, what my question is, but there's something that I have seen in the literature, but I don't know who wrote it. And I thought it made a lot of sense, because when you use the, what is it? The information criterion, what's those?
Akikes?
No, not
No, a different
not
information.
Komodorov. Which one do you say?
I said the Akikes or Akaikes information criterion.
No, the
No,
other,
a different one.
yeah, the way of choosing a model. and it's in the Ginsberg book, and
Okay.
but it's not symmetric. It's not
Oh,
symmetric. Whether you
okay.
have two models, it assumes one is, one and the other is something else. But I saw somewhere where somebody made it symmetric, and I thought that makes so much sense. I don't know the author, and it was probably in a paper that you'll never find normally. But it made, I think a lot of these things that we do, I'm thinking of I'll think over lunch, then I'll be able to tell you what I was
you'll
talking
remember it
about.
later. That's what happens to
Yeah.
me.
But it's true, I somehow see some very obscure papers that to me I think make most sense and nobody knows about them. And that's I wish I could find this paper again. It was published probably about 4 or 5 years ago. And I can't, not knowing the author, I can't look it up. But it made so much sense. If you look in the Ginsberg book, it talks about comparing two models, and whatever that criterion is not symmetric. But somebody I read made it symmetric, so it doesn't matter which is the null, which is the alternative. You're just comparing two models. And
that's
to me,
cool.
To me, they should be symmetric. It shouldn't matter which is the first and which is the second.
Right.
But the typical way that statisticians do it, it does matter. And it never made any sense to me. So over lunch, I'll try and think what that, I can look in the book. And
Yeah.
And tell you what I'm talking. Kolmogorov? No, not Kolmogorov. I don't know, but I'll get to it. But it to me, I don't know. I like things that to me make sense. and a lot of stuff that's done in statistics doesn't make too much sense. I mean, the BIC, the Bayes information criteria doesn't make any sense at all because it penalizes you for having a large sample.
Right.
Absolutely ridiculous. And people try and get around it and tell me this, that, and the other. I'm sorry. If you're going to penalize me for having a large sample, I ain't going to use your method. I mean, it's as simple as that. So, and I encourage people to think what they're doing, not just do it because everybody else does it, and certainly not do it just because I do it. Think. All right, let's have lunch, and we'll see you all in an hour or so. Is that right? Just about a little under an hour.